Welcome to Bridge the Gap, the physics-oriented podcast of the TU Graz,
where we give insight into physical topics and the life of scientists.
Hey Daniel, do you know what PhD stands for?
What does it stand for, Tommaso?
Well, it means patiently hoping for a degree. I mean, I have the impression that so far we had to endure a lot of frustration during our research years, right?
Well, I can't agree more.
So yeah, I'd say definitely patience is a requirement for survival, don't you think?
I fully agree with you there.
Okay, but anyways, welcome to Bridge the Gap, the podcast in which we try to explain complicated topics of physics by boiling them down to their smallest bits so that everyone can digest them. And today we'll be talking about some particles and quasi-particles.
What are quasi-particles?
Well, I don't know, I think all in all, they're topics of particular importance, right?
Right.
But also, we'll talk about electrons and their social habits.
Social habits of electrons? What does that mean?
Well, for example, do you know how electrons like to party?
No, how do electrons like to party?
Well, exclusively, of course, one at a time.
Yeah, now it makes sense.
Does it? Okay. Yeah, I mean, I feel the need to explain this. Electrons are particles that cannot be in the very same state, right? So, yeah. Of course, they like to party individually.
Sure, yeah, clearly.
Clearly. But I mean, the other reason can be that given their negative vibes, they will always push other electrons away.
Well, but thanks anyway for explaining the joke. That always makes them better.
Yeah, right. I know. You have to explain them. They're not as fun.
As we did in the last episode, we asked some of our students and friends for their intuition regarding today's topic. So before we start the podcast, here are the answers.
Apparently, most of them interpreted this question on a planetary scale. Today, however, we will discuss many-body physics on a quantum level. Most of the remarks made, however, describe the fundamental issues quite accurately.
Many-body physics is the study of multiple particles which interact with each other, and that's also the reason why it's so difficult, because every particle influences each other particle.
What comes to my mind is the free body problem, which is like you cannot predict the movement of free bodies in space because they behave chaotically and you cannot simulate or calculate accurately how they will behave.
And I have no clue why is it so difficult to deal with it. It's the first time I'm hearing about it, and my guess is that many-body physics has to deal with how multiple objects coexist and influence each other into space. For example, planets or galaxies that coexist altogether into our immense universe.
One of the most outstanding results of the early quantum mechanics is without doubt the description of the energy levels of the electron in the hydrogen atom. Now, hydrogen is the simplest element there is. In fact, it consists only of two particles. A proton, which is positively charged, and an electron with negative charge, which, air quotations, orbits around it. Let alone hydrogen, though, all the other elements have many electrons, so to describe them, one needs to understand their mutual interaction.
This brings up a whole new set of questions, the first of which is related to the so-called statistics of the wave function of many electron systems. Now just imagine what happens when one needs to describe a material with many atoms. That is, with many electrons as well, of course. If one does not resort to some sort of approximation, the result will become a headache guaranteed.
So today with us to shed light on this and other topics, Markus Aichhorn, professor at Graz University of Technology. So Markus, hi.
Hi, thanks for the invitation.
Thanks for coming. What's the difference between one particle and two-particle physics? What can you tell us about this?
Okay, so of course the difference between one and two particle physics or two body physics is coming from the quantum mechanical nature of particles. This is something which is not so straightforward to understand because quantum mechanical particles, if they're very microscopic, they behave just very differently to classical particles. Now, the key word here is that particles at this level, quantum mechanical particles, are not distinguishable from each other. Yeah. So imagine you have a billiard pool table and you have billiard balls there, which all have the same color. So you might say, okay, this is not distinguishable. So they all are the same. I cannot say which is which. But you have, in principle, the possibility to tag names to these balls, right? So you can say ball 1, ball 2, ball 3, ball 4. even without doing that, you could in principle. Now with quantum mechanical particles, this is not possible in principle. Yeah, there's just no way of saying this is, let's say, electron number 1, this is electron number 2, this is electron number 3, and the first electron is at this position and the second electron is at that position, because this concept is not useful, right? So if we want to describe quantum mechanical systems, we have to set up wave functions or the state variable for the system for the full system, which means for 2 particles, for instance. And then these wave functions need to fulfill certain properties, like they have to be what we call symmetric. Yeah. So the state of the system must not change if we interchange 2 particles. That makes it indistinguishable from each other. And if this is the case, if it's symmetric, then we call them bosons, for instance. Yeah. If the wave function is antisymmetric, so if there is a sign change involved in all this mathematical convolution, you get a fermion. Yeah. So where do these names come from? Of course, from physicists. So fermions come from Enrico Fermi, he did not invent this, but he was one of the founders of the so-called Fermi-Dirac statistics, which is exactly describing these particles. And bosons come from Bose. Bose was a very famous Indian physicist. There's the Bose Center in Calcutta, a very famous research center now. And these are called bosons. Yeah, you might have heard of the Bose-Einstein condensate, which is a macroscopic phenomenon. So it's a macroscopic effect that you see due to microscopic quantum mechanical origin. I will not go into detail for that, but it's a manifestation of quantum physics that you could see somehow. Yeah, still with a very inexpensive microscope, but you could see. Now with fermions, it's a bit different, because what this implies is that 2 fermions, they must not really meet each other. Yeah. So fermions, what we say or how we describe is, we say fermions cannot be in the same quantum mechanical state, because that is excluded by this property. And this is what we call the Pauli exclusion principle. Yeah. So again, related to Pauli, a very famous physicist, he noticed that if you have 2 fermions, they cannot be at the same place. Yeah. And this is then the so-called exchange hole. This is just a name that I tell you now, that due to the statistical features, 2 quantum mechanical particles cannot meet. It's not that they have forces between them or some electrostatic or gravitation or something. It's really the statistics of the particle that forbid them to meet. Yeah, that is a fermion. And in that sense, these 2 particles behave very different from 2 classical particles. Okay, classical particles also they can meet, they can collide, they can scatter off each other. They cannot be at the same space-time point, of course, because it's matter. So it needs to be somehow a bit different. But they can meet in principle, yeah? And you can say this is particle 1, this is particle 2, they scatter off each other, fine, yeah? This is Boltzmann statistics. We had Boltzmann, the name, last time. That's classical statistics. Now we have Fermi and Bose statistics. That's the quantum mechanical variant. So in that sense, if you have more than 1 quantum mechanical particles, it really gets quantum. Yeah. So with 1 particle, yeah, you could still say it's a fermion, but if there's no second fermion around, so what? I mean, there's not much to it. But if you have 2 fermions, things get interesting. Yeah.
Could you give some example for fermions? What exactly are these? What are the particles?
Electrons. Yeah. So this is the most famous fermion. An electron or a proton or now it's getting difficult. There are many fermions, but not so many known fermions, let's say. If you want to have a definition, the fermion is the one that has a half spin. Yeah, so where the so-called spin quantum number is 1/2, 3/2, 5/2, and so on. This is called a fermion. Now, if the spin quantum number is integer, like 0, 1, 2, 3, 4, then we call it a boson. We don't call it a boson. It follows that these particles have bosonic character. Yeah, and a neutron is still a fermion. Yeah, but if you have composite particles that are built up by 2 protons, 2 neutrons, 2 electrons, like atoms, helium, for instance, the atom as a whole might be a bosonic particle. Yeah, it has bosonic properties. Yeah.
You mean because of the overall spin quantum number?
Yes,
in this case,
because
you're
have
summing up all the individual bits.
Exactly. You have to sum up all individual bits and pieces of spins and also angular momentum and stuff. So there are many ingredients, and also the summation is not so straightforward as you might think, but you can sum it up. And if at the very end you get S equals 0, no spin, it's a boson. Yeah, it's a spinless boson even. Yeah, which is a quite special particle. Yeah, it's nothing very common.
Mm-hmm.
And why is it so hard to simulate a large number of fermions or electrons more concretely?
Mm-hmm. So that has to be specified a little bit what you mean by simulation, because what you mean by simulation is a classical simulation of a quantum mechanical system, I think. Yeah?
Yes, exactly.
So there, the quantum mechanical nature of these microscopic particles leads to the fact that a classical treatment is complicated. Yeah. And why is that? Because you need to think of how we describe these systems. And what we normally do is we describe a system or a particle within a certain phase space. Yeah. And for quantum mechanics, this phase space is what we call a Hilbert space. Yeah. We don't need to go into the details, but the decisive thing is that we need to find first all possibilities of states, so to say, where this particle can be in, or the system can be in. Now, let's make it simple. Let's say we have just one electron with the spin. Spin 1/2 means it can point either up or down. Yeah. So that's the internal degree of freedom of the electron. Now, if you have one particle, there's two possibilities. That would mean then in mathematical formulation, the dimension of this problem is 2, which is small. Now, if you add another particle, you have 2 times 2. It's 4. It's still nice. Yeah. Then you have a third particle, you end up with 6. You have 4 particles with 8. And then the COVID pandemic has told us that humans cannot think in exponential terms, but that's exactly an exponential problem. So it goes like 2 to the power of n, where n is the number of particles. And if you do these calculations, you see that it's fine for 20, maybe 30 particles, but then you hit what one might call the exponential wall. So the problem becomes increasingly complicated to even put on a computer, let alone doing some calculations. But you have to treat objects that are huge. That means they need gigabyte, even terabyte of memory on a classical computer. And then it comes to the point that it's not feasible to do it on a classical computer simulating a quantum mechanical system. Yeah. Another reason for that is, this is a nice way of interpreting that, quantum mechanics is giving you something that you might call an extra dimension to the problem. Yeah. So if you think of a one-dimensional problem, like a chain, you have a chain of particles, whatever they are, it doesn't matter. If you treat it classically, it's a chain of particles, sure. But if you include quantum mechanical effects to that, you get an extra dimension, which we call the quantum mechanical time, so to say, which is not the real time, but it's what quantum mechanics produces. That's these fluctuations that are intrinsic to the system, which then lead to this uncertainty principles and all this stuff. But you can think of an additional time domain where the system can go through. Yeah. So instead of having one dimension, you have 2 dimensions. Instead of having 3 dimensions, you have 4 dimensions. It's always this +1. So a quantum mechanical 3-dimensional system is kind of equivalent to a classical 4-dimensional system. That still does not explain the exponential wall, but that's another complication that you get from quantum mechanics. Yeah.
So this fact that you mentioned that you add another extra dimension is related to the fact that you're actually summing up over some more possibilities for these particles, or that
Exactly. That's again related to the probabilistic nature of quantum mechanics. It means that you start from a state of the system, so call it an initial state, and then quantum mechanics evolves that state, yeah, and goes into any possible state for this system with some probability. Yeah, this is at least the way of thinking is going back to Richard Feynman. Yeah, so he invented this formulation in terms of path integrals. That was the name that he gave this theory. And the path integral formulation of quantum mechanics is exactly doing that. It starts from one state and then sums up all possible trajectories to a final state and weights it with the corresponding probabilities. Yeah. And there was also saying that or an anecdote. When Richard Feynman invented this, he was really young. He was also doing his PhD, I think, so he was not even 30. And he went to Freeman Dyson, one of these famous solid-state physicists at the time, and told him, I invented this way of, this quantum mechanics. I know how this works. And then Dyson said, you're completely crazy. But in the end, it turned out that he's not crazy. Yeah? So now we know that this way of thinking is, in fact, valid. And it even is a natural explanation of what quantum mechanics is doing. Because if you sum up all trajectories, or put it differently, if you take the one with the highest weight, which we call the mean field solution, that would be a classical trajectory then that the system follows on average. Yeah? So there's a very natural explanation of quantum mechanics with the quantum fluctuations in terms of these path integrals. Yeah? And of course, this is also valid for one particle, but one can extend this description also to many particles, to the so-called many-body problem, and also find a path integral formulation or a functional integral formulation then for this many-body problem. Yeah. But it's just a different way of treating the quantum mechanical probabilities in a mathematical treatment.
So what can this be used for eventually? Because one can do simulations of many electrons, but what for exactly?
Of course, if you do simulations, you want to understand reality, at least ideally. Yeah, you can do also simulations because it's nice, but at the very end, you want to understand how things work. And one of the problems where you can apply these quantum mechanical simulations, at least that's the topic that I'm more familiar with, is if you go into materials properties. A material, by definition, is a many-body problem, right? So if you don't think more in detail of all these ingredients, at least you realize there are more than one electron, there's more than one atom. You have to build crystals. Ideally, it's a crystal without imperfections, so with periodic boundary conditions and everything is nice. But still, 1 mole of a crystal has 10 to the power of 20-something particles, which is, given that all this is exponentially difficult, very complicated. Yeah? That also means that we cannot do these classical simulations just without further thinking for a real material. It just doesn't work. It's impossible on the normal standard computers. And I think we will not go into the discussion of quantum computing at this point, because that's a very different avenue, but let's stick to classical simulations. So one needs to do something to treat this problem, right?
So you need to resort to some approximate scheme, you're saying?
Yes. Approximations.
Yes.
And for example, that was what has been done very early on when material science or solid state physics, let's say, was invented or started to be important, is that you still treat electrons as non-interacting, for instance. Yeah, we know that there are many electrons, but in many cases, it doesn't really matter. It's related to the fact or to the question, do the electrons that are in the material, do they meet each other or don't they? Yeah. If they don't meet, in a sense that one electron, although there are many others, it can just travel without seeing them. Yeah, it would be you are in a dance hall, but there are not so many people there, and it's dark, and you close your eyes and you dance and you meet nobody for the entire evening. You would think there was nobody there. But maybe there were 10 other people or 20 or 100, doesn't matter, but you don't meet them. So you feel alone. The electron likes that. We normally don't like that, but an electron likes that because it just can do what it wants. Yeah? And that also means that it has what we then call good transport properties. It can go from A to B without disturbances, without problems, and that's a good metal, for instance. Like,
so let's call it a metal. Yes.
Let's call it a metal. It would be perfect gold, perfect aluminum, copper, iron, whatever. In first approximation, this is the picture that you would draw. Yeah, there are electrons, they are dispersive, what we say. So they go from A to B, they carry transport, so current, electric current. And it's fine, yeah? The electron is an electron. Now, the thing changes when electrons get more dense. Also, the population gets more dense. Again, the analogy with the dance hall. If things fill up because the DJ is famous or something, then you start feeling each other, maybe to the point that you're stuck, right? It's so full that you cannot move. And this also can happen to electrons. And We don't like it. Electrons don't like it. So you're stuck. And when electrons or these charge carriers that carry normally the current, when they're stuck, it's an insulator. Yeah. And this analogy or this picture is the, at least in our community, famous Mott insulator. Yeah, it's an insulating state that cannot carry us or charged particles from A to B by applying a small electric field. This doesn't work, yeah, because there are so many other electrons, and in addition, now it's not just the Pauli exclusion principle, it's also electrons, they are charged, yeah. There's a Coulomb repulsion between these particles. They cannot just go around each other, they're stuck, and that's why they cannot conduct electrical current, and that's what we call an insulator. Yeah.
There's an interesting follow-up question, at least from my point of view, because now we're talking about first single electrons, which don't feel one another and they can go about doing their business and do whatever they want. Then we have the interaction picture in which electrons start to feel one another, maybe up to the point in which they're stuck, and then you have an insulator. So how does the picture from this, very definite particles that we call electron then become normally we say in the community quasi-particle, right? So how does the interaction changes the picture? What is a quasi-particle? So that's my question.
Yeah. So starting from a single electron, the quasi-particle, if you start with this limit, is the electron. Yeah. So if you don't have interactions, there's no such discrimination between a particle and a quasi-particle. Everything is a particle and the electron is an electron. Now, again, the dance hall analogy, if you don't pack it like crazy, densely, but just loosely to the point that you feel that there is somebody else there, what you do naturally is you try to avoid these people, at least normally. If you're not a sociopath, you try to avoid the others and try to go around them a bit and follow a path that is completely free, but is a bit constrained to what the other people do, but still you go around. You can do this, you can do that. And in that sense, you're still a person, but with slightly modified properties, like you're not completely free to move at the speed that you want. Maybe you're slowed down or you have certain directions where you cannot go anymore. And again, this happens to an electron, right? So there are other electrons around and they say, no, if you want to go to my direction, I'm already here. So please don't do this, go somewhere else, yeah, in simple terms. And this is what the electron is doing. And the quasi-particle description or the definition of a quasi-particle is then that we treat it as an electron. So assume that it's kind of free, but its parameters have changed. Like it gets more heavy, that means it's slowed down, or it gets a different property for the spin, so the magnetic susceptibility, so how this property or how the electron reacts to an external magnetic field changes, yeah, by the presence of surrounding particles. This is what we call a quasi-particle. And in this very simple picture, which in the very end is not true, but thinking of that is very easy. If the particle gets heavier, at some point it gets infinitely heavy and then gets stuck again and then it's insulating. Yeah. So you can connect continuously from the free particle, which is just not renormalized. It just is what it is, to the insulating particle that is just infinitely heavy and cannot move anymore. And that is one of the possible pictures of the Mott insulator, which is driven by some approximations which are what we call local in nature. Yeah. So if we treat this better and more properly, we know that the mass does not diverge, but still thinking in these terms is easier as an analogy. There is an interesting problem where the name quasi-particle basically comes from. That is the Kondo effect, for instance. Yeah. Right? This is also a very good example of how experiments and theory working together in material science to find out what's going on, because the Kondo effect was known for quite some time. And simply speaking, it's an anomaly in the resistivity of metals. We said metals have good conductivity, means low resistivity. And there's a very specific dependence on temperature. So we know that the metal has very good conductance, so it can conduct current very good at very low temperatures. And then when you heat it up, there is electron scattering, it produces resistivity, and the resistivity goes up with some power of the temperature. It doesn't matter so much how exactly. But now if you give imperfections into this material, like you put some iron into the gold or some zinc into copper or whatever, some imperfections, so impurities. At very low temperatures, something weird happens, or weird at first sight, namely that the resistivity first goes down, 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 and then at some temperature it goes up again. So it looks like an insulator, kind of. And this is what was known for a long time, the so-called Kondo insulator, and has not been explained by theory for many years. Yeah? And then Kondo, a Japanese physicist, he came up with a solution. Again, as usual in theoretical physics, the solution was in principle good, but the details were wrong. So the idea in the back was okay, but the treatment was wrong, let's say. So he said, okay, what's happening is that conduction electrons, they couple to this impurity and they couple to the spin of the impurity. Yeah? So iron has a so-called free spin. Yeah? It's quite long, S equals 2. So 4 electrons summing up to one large spin. And then this spin couples to the conduction electrons of the gold, so to say, and it sucks them out. So in simple terms, yeah. They are not there anymore for electric conductance, so they are missing, and that's why the resistivity goes up at this point, yeah. And this is what we now call Kondo screening, yeah. And that's a many-body effect. You cannot explain this just with effect that just treats the electrons there. There must be the electron and the impurity and the many-body coupling between the two. So they need to see each other, they need to feel each other, and then do this effect, yeah.
And why does this effect only occur at low temperatures?
That occurs because at high temperatures, the thermal movement or the thermal activation of electrons is large. Yeah? It's a quantum effect, and it happens just below a certain scale because quantum effects quite generally occur at rather low temperature scales where, as we talked before, the quantum fluctuations or the quantum effects become dominant. And thermal fluctuations and thermal effects get less and less and less important. Yeah? Quantum effects and quantum fluctuations you also have at T equals 0. If you have a classical system at 0 temperature, it's stuck. Nothing moves. That's the death of the universe, so to say, 0 temperature, nothing moves. But a quantum mechanical system does move at 0 temperature. Yeah? It cannot be completely at rest. It fluctuates, it has 0-point motions and all these kind of things. And this then gives rise to these quantum effects that you see at low temperatures. And for the Kondo insulator, it's the famous Kondo temperature. Yeah. So if you go below this energy scale, it's a typical temperature. It's not a phase transition, but it's a typical temperature where you go below like 50 Kelvin, 30 Kelvin, that are typical numbers, or even 10 Kelvin. You see this screening and you see the effect on the resistivity and then on magnetic susceptibility and some follow-ups. Yeah. So it's a complete effect that is relevant for many, many properties then.
So the bottom line is when you put a bunch of electrons and you put them together, the physics also changes. It's not just,
it might.
It might.
Not necessarily, but the physics of the whole system might change in a way that is not really expected from the individual electrons in total. Yeah. This can go so far that a completely new state emerges. I need to explain what emerging means. I think a new state can appear that is connected to this initial state of individual electrons, but really qualitatively different. Yeah, and this is what we call emergent phenomena. Yeah, emergent in the sense that it emerges like phoenix from the ashes, so to say, and produces something completely new that has not been there before. The most famous example is superconductivity. There are many, many other examples, but superconductivity many people know. So you put individual electrons into a material, and normally they conduct current as they do, as we discussed, with some resistivity. The resistivity gets lower when you cool down. But then at some point, it doesn't really become zero normally because there are some imperfections. So electrons scatter. But in a superconductor, at some point, below some certain temperature, the resistivity really drops to exactly 0 in a clean superconductor, the clean limit. And this means electric conductance with 0 resistivity. So if we use these kind of things for transporting electric energy, this will solve most of our energy problems, actually. The point is, this state, so the superconducting state, is not just the individual electrons summed up trivially, but it's something new. It's what we call the superconducting state. So that's then the Cooper pairs that do this. Yeah? Mm-hmm. And the Cooper pair is a combined particle. It's an emergent particle, if you say.
Or a quasi-particle. Maybe.
Or a quasi-particle. You can call it a quasi-particle. That is, if you write it down in formulas, it's a combination of two electrons. That's why this Cooper particle, at this point, it's a boson. Mm-hmm. So you start with fermions, but then the relevant particle that you look at
has a different nature.
Has a different nature.
Mm-hmm.
It is a boson. It can be, because it's a boson, more than one be in the same state, so it can condense. That's how we call it. And this condensation gives you the superconducting state. And this is a very typical emergent phenomenon that is new. It does not necessarily follow from the electrons. It follows also because we know that superconductivity exists. Again, experiment was before the theory. And now we understand more or less how superconductivity in principle works. For many superconducting materials, we still don't know why exactly. But at least this basic phenomenon of superconductivity, at least if you ask 95% of the community, I think it's agreed on how this works.
Mm-hmm. So since you mentioned the study of materials, what is exactly your expertise, your field of expertise, your line of research?
My personal expertise is exactly what we were discussing with these classical simulations of quantum mechanical systems. So what we do in our lab is trying to understand these properties of materials like resistivity or magnetic susceptibility, temperature dependencies of properties from computer simulations. And then in most of the cases, we try to find explanations for experimental data that is already there. It's a matter of fact that in our community, new developments are to 90% driven by experimental discoveries. So people go to the lab, they try to change an existing system, find something new, and then sometimes just by accident, guided accidents, let's say, it's not that they just do whatever they want, but they have some certain ideas and then it works. And then they get some new properties, some new superconducting materials or some new excitonic insulators or spintronic devices, whatever. And then in theory, we try to use our tools, our approximations and methods to understand that. That gives then a new twist for new experiments, maybe.
Mm-hmm. How well does this work to explain the real experiments with simulations? Are there some issues sometimes, or is this always working out good?
Oh, there are many issues. So I think there is no general answer to that because that depends a lot on the field. So the biggest and I think most successful field comparing computations and experiment is the field of weakly correlated materials or even non-correlated materials or chemistry. Yeah, where a very famous theory that we call density functional theory, that famous, we should not call him Austrian because he's a US citizen, Walter Kohn. So he was born in Austria but worked most of the time in the US. He found this theory in the 70s and that is applied to many, many, many systems with such an accuracy that was just unbelievable before. Of course, there are then some extensions to that and some new approaches that make that even better, but it works for so many materials just so nicely that it can be called the workhorse of materials science even, yeah. Now in the field that I work personally, which is correlated electrons, the situation is a bit more different because exactly this theory doesn't work. Density functional theory relies on the fact that electrons still are electrons in a sense, right? So we talked about these quasi-particles. If the electron is not changed too much by all these interactions and by the presence of other stuff in the material, this is fine, yeah. But as soon as these emergent phenomena come about, then this whole picture breaks down, or let's say the approximations that we need to do to solve the equations, that breaks down and we need to do other approximations, other methods, other algorithms, which are then more tailored towards this many-body and interacting problem. But they are so expensive that it's very difficult to simulate big systems, meaning a real crystal. So there are pros and cons to all of that. The bottom line is that for the complicated correlated materials, the accuracy that we can reach is maybe, 20%, 30% to experimental data, but we can study trends. We can say if we do this and that to a material, the resistivity should go up or down, or then we see this effect, sometimes strange effects, but we can give trends to experimentalists and say, try this out, press it, push it, replace this element by another element, and then we see what happens. We are not in the situation that we can reach what is called chemical accuracy. Like chemical accuracy means really calculating chemical reactions, reaction path, like activation energies and Arrhenius laws and these kind of things. This we cannot do. It's just out of the question, but we can do simpler stuff. Yeah. We can study general properties of materials and how they change when we change the material. This is what we can do. But it's still very complicated. It's very costly. It needs a lot of energy. So also
and manpower.
And manpower. Yes. So
an advertisement for all the students, like
please come to our labs. At least talk to us. And then we'll see if you find it interesting. It's a very interesting field. What I like about it is that the field is not huge compared to chemistry, for instance. So we know each other. We know who's working in these problems. We know also international colleagues. So it's a very nice network of people that is not just millions of them, but a few hundred or so. So we know many. And it's just fun to work in this environment.
Well, good. So I think on this positive note, we can end the episode. So thanks for coming.
Thanks for the invitation.
See you next time.
See you.
Thanks for listening.
And see you next time.